All right, welcome back, everybody. I hope that y'all didn't skip the warm up because we literally just talked about every single question that was going to be on the exam. Just kidding, but it is still really important for some of the skills that you'll need to know moving forward. So make sure you take a look at that warm up section if you haven't done so yet. But we will move on to what we will be going over today for new content, which is going to be a part of chapter 7. And I believe it also includes a part of chapter 8. Yes, chapter 7.2, 8.2, if you are somebody who likes to follow from the textbook, where we're going to be going over methods when the population standard deviation is unknown. Okay, so in all of our problems before, we've talked about how you can create a confidence interval or how you can find or you can do some hypotheses testings. But with all of those scenarios, we had the population standard deviation given to us. And honestly, it's sort of not the most real, I guess you could say, in like a real world context to know what the population standard deviation is. Because if you know the population standard deviation, it sort of implies that you would know what the population mean is in a way. I mean, if we think about that standard deviation equation, we're using the mean in that equation specifically. So how would you know like one and not the other in a real context? I mean, I guess you can make like an estimate, but let's be real, you're not going to know this in the real world. So these are things that are a little bit more relevant in the statistics world. And you may see these a lot in like your nursing articles when you go into like your evidence-based course as well. So let's go into these methods. I know I sort of talked about like these little theoretical things, but we're going to be talking about a couple of new vocabulary terms, degrees of freedom. We're going to be looking at a new chart when finding critical values because we're working with a new distribution, a student's t distribution. And then we're going to be in this section computing the confidence intervals. In the next section, we're going to be talking about how to do those hypothesis tests. Okay. Now, to go over some of the pertinent vocabulary, okay, the student's t distribution, as we read out loud here, is a symmetric bell-shaped distribution where the tails are more spread out than the normal distribution. So it looks similar to the normal distribution, but it may be pulled on both sides or maybe crunched up more on the sides. And I'll get into a picture of how that looks later, okay? When we use the t distribution and we use any of these methods, the population standard deviation is unknown. Okay. And that's bolded, underlined, underscored, everything. Okay. So you know that probably is something that may be important for you to know, even beyond just this lecture, if you're picking up what I'm putting down. Okay. So whenever you're talking about something where you don't know what the population standard deviation is, you automatically want to start thinking about the student's t distribution. Okay, the student's t distribution also includes this concept of a degrees of freedom. Basically, it's looking at the number of values or observations that the data is free to vary when estimating a parameter. The degrees of freedom affects how spread out the tails are on the t distribution. So basically, because now we're making a lot more assumptions, we have to denote how much freedom we're actually going to give to this new model that we're creating. Okay, and as we'll see moving forward, we're because we don't know what the standard deviation, population standard deviation is, that's going to be like that parameter that we're sort of estimating in this context. Okay, that's going to be the big one that we're really estimating. And I'll show you how that looks like in the equation for the degrees of freedom moving forward as well. Okay, look at the size of that font. That's crazy. Okay, let's read what it says. As degrees of freedom increases, the student's t distribution starts to become more like the standard normal distribution. Okay, that looks super, super, super duper important here. Okay, so let's break it down and see what it's actually saying here. Okay, if we look at the picture on the left here, that is denoting our normal distribution. And then we have two other distributions that look similar to it, but we have like a little bit of splaying of the tails. Okay, which is denoted as the t distribution. Okay, we have two different types of t distributions. This is like the t distribution, sort of like a gradient, you can say. It's not a specific one. And they vary by the number of degrees of freedom that you have in the t-distributions. Okay, so the black one is your 3 degrees of freedom, and the blue one is 5 degrees of freedom. Okay, and if we look at the trends for both of these graphs, or both of these graphs specifically, the blue and the black, the blue graph looks a lot more similar to the normal distribution, or the one in purple, than the one in black. Okay, this is visually showing us, like, in a way, the tails are getting tighter, specifically in the blue when compared to the black, and that maximum point, that middle point, you know, where that modal class is on that t distribution, is starting to come closer to the normal distribution at that point as well. So we can see in general it's looking more and more like the normal distribution, and this happens because our degrees of freedom increase. Okay. And I'm going to skip over to 2 slides down, and we can conceptualize this a little bit more when looking at the degrees of freedom equation. Okay, the degrees of freedom equation here is talking about how the degrees of freedom is equivalent to the sample size minus 1. That minus 1 is that parameter that you are approximating, okay, which is going to be that standard deviation in this case. Okay, that knowing it's a standard deviation part isn't the big point here. It's more just knowing that we're approximating one of the parameters. Okay, but that biggest thing that you want to remember here from the degrees of freedom equation is that the degrees of freedom is based on our sample size. Okay, now if we talked about anything in this class, it's always talking about how as you're increasing your sample size, you're including more and more individuals from your population. Okay, if your population is normally distributed and you're including more and more people from that specific population, then what you're inherently calculating is going to look more and more like the population. In other words, if you have a bigger sample size, it's going to look like a normal distribution more and more. And this is what it's telling us basically from a visual standpoint, and then it's also, now we're incorporating it with that numeric standpoint. Okay, so this is not telling us anything really too different from what we've been talking about before. A representative sample, a sample that is including more of the population, is going to look like the population. Okay, all right. I'm going to get off my soapbox here, and we're going to talk about another important concept that we need to learn about for the t-distribution here is the assumptions. You are going to be required to know the assumptions for a t-distribution test. Okay, so make sure to put these all into memory. The first one being that the data must come from an approximately normal distribution. You can't have any outliers in the sample set. Okay, and you have to be able to compute the sample standard deviation, right? So let's break down what these all mean a little bit to help you remember that these are the assumptions that you need. Okay, approximately normal distributed, that makes sense, but from this whole thing that we were just talking about. Okay, the t distribution is sort of building up to this idea of a normal distribution. It's a generalization of the normal distribution, you could say, right? So if you're increasing your sample size and it's starting to look more like the normal distribution, well, your sample has to be from something that's approximately normal, or that trend would not be showing. So that one makes a little bit of sense when we talk about the previous slide. Okay, the next thing is about no outliers in a sample set. Well, that makes sense too. If we're thinking about it from the stuff that we talked about in previous classes, where we have some kind of skewness to our distributions, then having an outlier is going to cause this skewness. It's not necessarily going to be helping us with a symmetric. If you have a really large data point, you want to have a really small data point to keep that stuff symmetric. Okay, so it's sort of going along the lines of that normal distribution point from point 1. And the last part is sample standard deviation. So this whole entire idea of this t distribution, students t distribution, is that you don't know what the population standard deviation is. How can you remedy that? By being able to find out what the sample standard deviation is and making some kind of approximations based off of that sample standard deviation. So you're doing some kind of standard deviation work with it inherently in this kind of process. But if you don't know it, there's no way that you can really use this kind of method as well. And in the real world, it makes more sense that you can calculate the sample standard deviation because you have the sample right in front of you. You have all the data in front of you and you can find it. So this last assumption is actually probably the easiest one of these 3 to figure out. at least when you have the data raw given to you. Okay, perfect. So now let's talk about our new t variable, okay? So the t variable is correspondent to like the z variable or the z-score, okay? We have different moving components in the t variable here. So let's break down what each of these different variables inside of this equation stand for, okay? We know this one already. We know a lot of these actually. This one is our sample mean, the x bar. We have mu, which is our population mean. We have this lowercase s. That's where our sample standard deviation comes into play. Okay, and we have n, which is going to be our sample size. Okay, and if you can't read my chicken scratch handwriting when I did all of that there, I also have everything written down on the bottom here that I'm going to color code right now for your convenience. Okay, now if we actually break down this t variable equation, it's not too different from the z-score equation, the one that we just did for our warm-up. Okay, again, if you didn't do the warm-up, go back and try looking at it because it's going to help you with like the setup for this problem in a way. Okay, just to rewrite what we had here, we had x bar minus mu over the sigma divided by the square root of n. The only thing that changes in this equation for the t variable is that we're using the sample standard deviation as opposed to the population standard deviation. Okay, this drills in this concept that when you're using the t variable and you're using the t-scores and everything, that you don't need to know the population standard deviation. Because if you did, you can just calculate everything using the z-scores. There's no point in going in and using this kind of problem where you have to make more assumptions, where it is a more generalization, and overall in the statistics world, it's a less powerful test when compared to the z-score. Okay, so just by a process of elimination there, I'm going to erase that there. Y'all get the vibe here though. Okay, t variable equation. Looks scary. Not really scary when we think about it as just being a different flavor of what we've been learning. Okay? We do have a new chart here though, and look at the size of the font on the right there. That's crazy. It's huge, ginormous, bolded, underlined. Let's read what it says. As the confidence interval increases, the critical t-value increases. Okay, so I'm seeing one increases, the other one increases. Okay, for confidence interval. And now if we look at the sample size increasing, the critical t-value increases. Now let's break down like what these specifically mean and using the chart, okay? So on this chart, let's break down the anatomy of the chart. We have 3 rows on the top in the bolded blue. We have a one-tailed area, a two-tailed area, and then a row for the level of confidence, which is denoted as that C. On the left, we have our degrees of freedom. Okay, so degrees of freedom is coming back. It's that sample size minus 1. If we think about that equation from above here that was highlighted in that beautiful pink. Okay. So as the confidence interval increases, the critical t-value increases. Okay, so that's going to mean that as we move from left to right, because as we see, we're moving from smaller to larger from the stuff we're underlining, 0.8, 0.85, 9, so on. The values inside of the chart which are the critical t-values, will be increasing as well. So let's look down one row and zoom in on row 3, for example. Okay. As we move from a level of confidence of 50%, we have a critical t-value of 0.765. To a 75% confidence interval, we have a 1.423. This number is increasing, showing that this trend, as the confidence interval increases, the critical t-value increases as well. Okay, let's look at the other one. All right, highlighted here in that wonderful pink. as the sample size increases, the critical t-value decreases. Okay? So if we remember back to this equation, degrees of freedom is equal to your sample size minus 1. So let's sort of pretend that the left side is your sample size. Okay, it's only just changing by one term. Or, yeah, one number, basically. Sample size increases, the critical t-value increases. We can look at it from any row standpoint. Okay, so if we look at this first row here, we're keeping that confidence interval the same. And all we're doing is we're changing the sample size from 2 to 3. Again, because this is 1 minus 1, because this is degrees of freedom. 8 to 9, and so on. So from 1 to 2 of degrees of freedom, or 2 to 3 from sample size, that number is decreasing. From a sample size of 8 to 9, or degrees of freedom of 7 to 8, that number is decreasing as well from 0.711 to 0.706. Okay, knowing these trends are going to be very important for your examination purposes, but it's great if you ever come across one of these kind of problems, because you can use the chart to help you figure out what that trend is going to look like. Okay, so again, to summarize, as the sample size increases, the critical t-value decreases. Okay, and that's denoted here in this chart on the left here. Okay, let's do a knowledge check. I'm going to have you pause the video here, and when we come back, we'll go over the answers for these. All right, welcome back. The first problem here is talking about as the degrees of freedom increases, what happens to the t-distribution curve? Okay. As the degrees of freedom increases, what happens to the t-distribution curve? Okay. This goes back to slide 8, it looks like. As we went from degrees of freedom to 3, from 3 to 5, we're increasing our degrees of freedom. We know that that becomes more like the standard normal distribution. Okay, so that's the big thing that you want to recognize here. Okay. As degrees of freedom increases, the t-distribution curve becomes more like the standard normal distribution. Okay. Big concept there. The next one here. State the relationship between the sample size and the critical t-value. Okay. Well, as the sample size increases, like we have highlighted here in pink, the critical t-value decreases. Okay? Those aren't going in the same direction. One's going up and the other one's going down. Okay? This is going to be an inverse relationship. Okay? So, in other words, as your sample size increases, the critical t-value decreases, and vice versa. Okay. Okay. So we have this new chart. Let's actually go through the steps for how to use this chart to find the critical t-values. So as we sort of alluded to before, the content inside is the critical t-value itself, and you're using the confidence interval and the degrees of freedom to actually do this. Okay, so the first thing you have to do is actually calculate the degrees of freedom, which is probably the easiest calculation that you'll ever have in this class. You're taking the number, subtracting 1 from it. Next, you want to locate the degrees of freedom on the chart with the critical t-value being somewhere in that row. Okay, sort of like how we did with the z-chart, where we found the first 2 numbers of the z-score. That was that first row, or that first column. Okay, and then we find it and we correspond it with somewhere in that row. The next part is a little bit different. We're looking for the targeted confidence interval. Okay, this is going to be our C value, right, our level of confidence. And that critical t-value is going to be the intersection between the row that was found in step 2 and this column. Okay, so same kind of process. You're finding 2 specific numbers, you're finding where they intersect, and that's going to be the number that you're looking for. Okay, just in a different font. Okay, so the wording for these kind of problems are going to be something that I want you to get very familiar with on moving forward. Okay, so let's do these kind of problems. Let's do the first one together, and I'm going to have you pause the second video, or if you're really feeling ambitious and you want to pause it now, then we can get more familiar with this chart. And that chart is going to be on the next slide here for the people who are pausing. So number one, use the student's t-distribution to find the critical t-value for a 98% confidence interval when the sample size is 23. The first step, as we see from this previous slide, is to calculate the degrees of freedom. Okay, degrees of freedom here is going to be equal to n minus 1, n being your sample size. That means that your degrees of freedom is going to be 23 minus 1, which is equal to 22. Now again, the easiest equation that you're going to have in this class. Okay, now that we have the degrees of freedom, we can now actually use the chart. So we're finding a 98% confidence interval. So the level of confidence, C, is going to be 0.98. Let's correspond the two together. Okay, I forgot it already. So degrees of freedom of 22. That's going to be in, we're looking at that first row there. Highlighted in green is the 22. And you look at that whole row. Okay, now you want to find the intersection of that value with a confidence level of 98%, which is 0.98, that I'm going to highlight here in this light pink. Don't worry about the one-tailed area, two-tailed area at this time because you're given the confidence interval. The intersection of these two values is going to be 2.508. Okay? And the best part about this chart that's a little bit different from the z-score chart is that because we're not calculating a probability, we're not calculating an area underneath the curve, we don't have to worry about adding or subtracting or nothing. The value that's going to be on this chart is going to be the value that we report, always. So this t critical value is going to be equal to 2.508. Okay. That's going to be our answer for number one. I'm going to have you pause this part here and try to do number two on your own. And then let's come back together and figure out what that answer is together when you're ready. All right. Thank you for pausing. Let's go into problem number two here. So we're going to use the student's t-distribution to find the critical t-value for a 95% confidence interval when the sample size is 18. The first thing you want to do is calculate your degrees of freedom. That's going to be your sample size minus 1. Again, we're doing a 95% confidence interval here. That means your degrees of freedom is going to be 18 minus 1, which is 17. Okay? You really, really, really want to make sure that you're doing the minus 1 problem because if you were to get a problem similar to this on the exam, one of the answer choices could be the row underneath it where you didn't subtract 1. So you really want to make sure that you're doing the right process there. Okay, I think I could see them using that as like an answer choice to throw you off. Next one is looking at the confidence interval. This 95% confidence interval gives you a confidence level of 0.95. We find 0.95 in the part that I circled right there, giving us this row as the row of interest with that column of interest as well. Our critical t-value is going to be 2.110. Okay, and again, you could write out the 0.95 there as customary if you'd like. If you were to be given this problem on the exam, they're going to really only focus on what number you get from the chart. So just for consistency's sake, we're going to write that out as t critical 0.98 as 2.508. Okay. Okay. I know y'all did great on this one. You guys are really great at using like these charts. And again, if something's confusing with this, send me an email. We'll get some office hours going. Or you can just rewind the video. Love having online classes for that. Okay. So now that we know how to use this chart, we can actually go in and try to construct the confidence interval. Okay. The first thing that we're going to do when constructing the confidence interval is calculate the critical t-value. Okay, that's going to be going in, finding the degrees of freedom based off of the confidence interval and using this chart. Okay, so it's not necessarily a calculation except for the fact that we have to do the sample size minus 1 for degrees of freedom, but we'll take any easy calculations in this class because we've been throwing a lot of hard ones so far. The next one is going to be calculating the margin of error. And as we know, that's going to be defined as the second term in the expression for finding the confidence interval, which we have written down on the bottom here. Because the third step is to actually calculate that confidence interval, which is going to be plus or minus whatever that margin of error is to your sample mean. And last but not least, they're going to want you to calculate or give your interpretation here. Okay? So if you want to try to do this one on your own, it's very similar process to how you would calculate the confidence interval for the mean when this population standard deviation is known from module 4, I believe. Don't quote me on that specifically. I think it is module 4. Yep, module 4. So same process, except you're using different charts here. So by all means, you can try doing this on your own. If not, continue watching the video here. So the problem is, a doctor wants to determine if a new diet plan significantly reduces weight loss after 6 weeks. The average weight loss in a general population without the diet is known to be 3 kilograms. A sample of 20 patients who followed a diet showed a sample mean of 4.2 kilograms and a sample standard deviation of 1.5 kilograms, and a population mean estimate to be 3. Again, so rewriting what was said on there. Okay, construct a confidence interval for the confidence level of 0.95. The first step here is to calculate that critical t-value. Okay. So the critical t-value, you're going to need the degrees of freedom and your level that you're looking for. So we have that. We have a new chart a couple pages down. Degrees of freedom is going to be equal to n minus 1. Our sample size is going to be this random sample of 20 patients. That gives you a degrees of freedom of 19. Okay. The confidence level was given to you as 0.95. So let's find where those numbers intersect on the chart here. Okay, so we have degrees of freedom of 19. That's going to be this one highlighted in red. And a confidence level of 0.95, which is going to be right there. The intersection of these two numbers is going to be 2.093. This is your t critical value, or 0.950 at 2.093. Okay. And I forgot to write out the step there. So the first step was to calculate the t critical value. Let's actually use the extra space slide for once, because our next step here is to calculate the margin of error. Okay, so the margin of error, well, if we write out the step, margin of error is the second term on the confidence interval equation. That's the critical t-value multiplied by the sample standard deviation divided by the square root of the sample size. Okay. Your critical t-value is the one that we found on the chart, the 2.093. And now we need to find out what the sample standard deviation and the sample size is. Okay, sample standard deviation here was stated to be 1.5. Let's do the color coding system again. And we had a sample of 20 patients, which is our sample size. Okay. Let's color code everything that we see on this part of the equation here. This is going to be 2.093 multiplied by 1.5 divided by the square root of 20. Let's see here. Square root of 20 is going to be equal to 4.472135. So I'm going to round up that 3 to 4. I'm going to do everything in the parentheses first. So 1.5 divided by 4.47214. That's going to give us the number inside the parentheses to be 0.3354. It's 0.9, so I'll put 1 as the last number there. Okay. 2.093 multiplied by 0.33541. Multiplying these two numbers together, we get a margin of error of 0.702. I like to report that one to the 3 decimal places. Okay. This next step here is to combine that number that we found to calculate the confidence interval. That equation is going to be x bar plus or minus the margin of error, which I'm going to denote as E here because we just calculated that in step 2. And we need to know what the sample size, the sample mean was. On this equation, it said that the sample mean is 4.2. So we're going to take 4.2, add or subtract 0.702. Okay, add or subtract, that's going to give us two answers, the subtraction answer and the addition answer. We're going to write it out in the form of like a coordinate point. Is like the customary for it, or you could just write out both as it is. 4.2 minus 0.702 is equivalent to 3.498. And if we add that number instead, we will get 4.902. Okay, this is our confidence interval, which usually is like the end of the problem, but let's, for completeness sake, let's give the interpretation. Okay, so the interpretation I have written out in text on the bottom here. We're going to fill in the blanks here. We are blank percent confident. This is asking for what the confidence level was, and you want to write it as a percentage. So we are 95% confident that the population mean for weight loss mu is within the interval of, write your lowest bound for your confidence interval, 3.498 to 4.902. Okay, and that is a successful conclusion to your confidence interval for this problem. Okay. In the next video, we are going to explore the hypothesis tests for this kind of method. And just for completeness here, they did give you more information than you needed for this problem. I wanted to do that to throw you off a little bit because I'm mean, but also just so you are a little bit more confident with your answers, that you're doing the right process. But on your examinations, they're really just they're most likely only going to give you what you need. So sorry for being a little mean there, but we got through it just fine. All right, next video is 8.2.